Good day, folks. Some people were asking about details of my big coil, the famous big coil here that worked very well for the back EMF projects, for the solid-state Bedini projects I had about a year ago. So while taking it out to inspect it, I came up with a new design for it that works very well, and I'll explain it. So first, the coil here, people were still asking about it. This is just a spool of telephone cable that I found at it was Value Village, and there was about this was a 200 foot, and there was about 50 feet of it that was already used. So give or take about 150 feet here of turns. And all I did here was I twisted all of the wire. They're twisted inside here. It's 4 wires, and I just twisted them all together to make one big wire. The impedance is 0.9 ohms. So what seems to be very important in these projects here for the inductive kickback is to have the lowest impedance and the biggest mass, big, heavy, like 20 pounds or more, transformers, heavy mass. So anyways, that's the coil, nothing special there. So I was looking at the Bedini projects, and in my earlier projects I was using cap dumps, and I'm using 1 UF, I'm using 22 UF, and I'm really happy when a 22 UF from the inductive kickback gives me like 3 dumps a second. As good as it is, it's still pretty little current. And as soon as I tried to put big capacitors, I wasn't getting the rate. And I'm looking at the Bedini devices, and he's got really huge capacitors, and I'm trying to figure out why does he have all those big input and output capacitors. So it got me thinking here. So after I tested this, it worked well, so I decided to make a real version of it here, and then I'm actually using, because it works so well, I'm going to show you folks this. So a little different here. Here's the pulse generator, which is a switch which controls a transistor with sharp spikes here that I can control with the pulse generator. But what I'm doing now is, instead of just pulsing the raw power, I'm first charging a big capacitor here. This is a 20,000 UF 40 volts DC capacitor. And what I have here, which seems weird, is a power bar here with 2 power supplies. I'll explain this. And in some earlier videos, I think it was Tachyon Catcher, I was having problems with isolating the input and the controller and the dump and all of that. And I was getting interference, and one module only needed a little bit of current, another thing needed higher power for the back EMF dump, and I just would semiconductors and voltage regulators and all that, either I would blow them up, or they'd be out of rating, or I'd be using too much current. And I believe it was Tachyon Catcher, I'm sorry if it's wrong, but I think it was him, that said, stick with magnetics. Tesla had magnetics back in the day. So to limit current, to control voltage and all that, he used magnetics. So that got me thinking. He said, you know what? That's what I'm going to do here. So one little tiny power supply, traditional, no switching, just a real transformer here. And this is AC to DC, and this one here is just a 12 volt 200 milliamp to control the controller here, which only uses about 30 MAs. So this is very little power and goes in line with what I'm trying to do to keep the input very, very low. And here's a second DC power supply here, AC to DC, traditional non-switching, which is what we want. We want to use just magnetics, and this isolates the two, no problem, easy, simple. This eliminates a lot of circuitry and parts, and it gives us really good efficiency. And of course, this one here is higher power. I realized that instead of pulsing 12 volts, if you bring that voltage, the pure potential, higher, you get much more inductive kickback. So I tried first with the power supply direct, and it was pretty good. And this is when I had the idea, you know what, I'll use this to charge the big capacitor and then pulse the capacitor through the switch into the coil. So what we're doing here is we're pulsing the cap. So we're actually charging the big cap. We're dumping it. It's a cap dump in essence, but we're dumping the cap into the coil here, and that's giving us a greater back EMF kickback, which charges the battery really nicely. And this is why I want to keep this, because in all of the projects I've done, I think this one here is the most efficient, uses less current, and really has a kick. And to explain here what happens, I'll try and explain it. So a battery, like even a larger one, like a car battery with a higher current rating, it typically delivers its power more steadily and over a longer duration. So the batteries are designed for sustained energy delivery rather than rapid discharges. So even if the battery can provide high current, like I thought of, instead of using the capacitor, use a couple car batteries, but maybe not because of this. Even if it's high current, what I'm getting at is the internal resistance and chemical properties and everything else will limit the rate at which it can deliver, the current in a sudden spike. Now, capacitors, on the other hand, the capacitor basically stores its charge in the electric field rather than chemical reactions like the batteries do. So when they're discharged, you know what I'm saying, they can release, if you let it, its entire stored energy almost instantaneously. That's where we get the amps a second discharge, or the joule. So that results in very high current spike for a very short duration, exactly what we want to do to trigger the inductive kickback. This really highly amplifies the amplitude outputs of the back and the current. So basically, the strength of the inductive kickback is related to the rate of change of current through the coil, basically. So when the capacitor discharges through the coil, it can create a much faster and larger charge in current than the battery can. So this rapid charge results in a stronger magnetic field being generating and then collapsing, which in turn produces more powerful inductive kickbacks, which charges the battery here. So basically, what I'm getting at is, if we're looking to create a strong inductive kickback using a large capacitor like I'm doing here, with the help of Bedini, which he was doing as well, charged basically to the same voltage as a battery that would be used to trigger it, this will yield a significant back EMF spike than using a traditional battery. So even higher current output. So I tested this, and sure enough, it's working really well. And I've got a magnet on here because I could hear it humming, so it gives me an indication if it's working well here. And people keep asking for circuit diagrams, so I actually made the circuit diagram here. I'll try and get a good view on this so you can see it. So what happens here is our two transformers here. So one of them is the T1 and the T2 transformer, traditional electromagnetics. And we're using the 12 volt low current to run our pulse generator, which is running this NPN transistor MJL21194G over here and here. And this switches the capacitor here through our big coil here, and here's our reverse diode for a charging output. So relatively simple circuit diagram. As you can see, sticking with traditional electromagnetics really simplifies and takes away a lot of headaches and makes this work very nicely. So let's turn it on, right? So I'm going to show you the charge of the battery first here. So 8.30. So I'm going to turn the power bar on here. So now we're running, but look at how quick that battery, look how quick that's climbing. This is a dead battery, by the way. Look how quick that's going. And we're using milliamps here. Maybe 10 here and 30 here. We're actually using more for the pulse controller than the power we're using. There's an initial spike, right, to charge the big capacitor. Once it's charged, it's like building up a pressure, and then we're shooting the pressure off of a very tight small hole, and it's shooting very, very strong, and that's what we're doing into the coil here. We build up the pressure to the capacitor, and it's this pressure that's giving us the, look at that, 8.66 already, 8.67, and my meter wants to go to sleep. 8.68. I actually got to watch it because at about 9.5 it's going to be overcharged. But see how quick it's happening? Just a few minutes, folks. So the frequency right now is 314 Hertz at 6%. I've tried it all, and this seems to be the sweet spot. Below it charges slower. If I start raising it, the charge goes down. So it's all about finding the sweet spot to saturate your coil, and you stick with that. And you don't need any more than what you need. And if anybody's wondering about the bias resistor, it's anywhere from 1 to 100K, basically, depending on what your inputs are. Mine here is around 90 for this setting. If you could always use math to figure it out exactly. If you don't want to use math, use a variable resistor, and test it, use a meter and pass the negative through the meter, read the voltage, and slowly bring the resistor down right until the voltage starts to drop. Then bring it back up a little, right to that point, and it'll be exactly fine-tuned for your system for maximum saturation, but not oversaturation and not undersaturation. And you could really hear the magnet humming. This gives me an indication and how strong the field is, because it hums even away from the coil. So far best setup, folks, and it really flies for charging batteries. So I'm keeping this one here as a prototype and to use personally because it works so well. So again, I hope you enjoy, and just putting out hints out there because a lot of people were asking for it. And usually people ask for circuit diagrams, so I made the circuit diagram on here as well. So until next time, folks, and thank you for watching, and let me know what you think in the comments.